Yes, sir. Fine.
We'll start our session within 2-3 minutes, sir.
Sure, sure. Please do let me know whenever I have to do it.
Hello, Mohit sir. Hello. Hello.
Hello, Unde sir here, sir.
Now we can start the session.
Okay, sir, no problem. Can you hear me, all of you?
Hello, sir.
Yes.
Pandey sir. Pandey sir.
Yes, yes.
Now we can start our session.
Okay. Shall I do it?
Just a minute. I
I think your
Sanket, your
voice
voice is
is
not
little
audible.
bit.
Your voice is not audible, Sanket.
afternoon for all of you. I assumed all few days my program.
Now it's audible.
Yes, yes.
Hello.
Yes, you can start now.
Very good afternoon, all of you. I am Professor Sanketunde. Welcome you all for 5 days faculty development program on recent advances in mechanical engineering design, organized by Mechanical Engineering Department, Bharati Vidyapeeth, deemed to be University College of Engineering, Pune. For the today's third session, we have with us dynamic and motivative personal, Dr. Ashok Kumar Pandey sir. Dr. Ashok Kumar Pandey sir received his BE in mechanical engineering from Ravi Shankar Shukla University, Raipur in 2001. Further, he received his MS and PhD in the field of mechanical engineering from IIS Bangalore in 2003. After completing his postdoctoral research work from Techno Israel Institute of Technology, Israel, at the present, Dr. Ashok Kumar Pandey is working as an associate professor in the Department of Mechanical and Aerospace Engineering IIT Hyderabad. His research area of interest are linear, non-linear vibration, vehicle dynamics, MEMS, and NEMS, based sensors and actuators. Uh, he is a member of professional bodies like ACA, IEEES, MRS, SPIE. He has published 57 research paper, 2 book chapters with citation of more than 1000 with H index 18. uh, he was awarded Hetnia Award 2010 by Society of Experimental Mechanics for effect of pressure on fluid damping in a MEMS torsional resonance with the flow ranging from quantum to molecular region. I welcome you, sir, and request to take the charge of this dais and enlighten the participants with your words.
Thank you, Professor Unde,
Thank
for
you.
a nice introduction. And it's a pleasure to be among all of you. And thanks for the kind invitation. And we know that your institute is also very good, and they are doing good. So it is always a pleasure to interact with your faculty member and other faculty members participating in AICTE FDP program. So in today's session, I'll be talking about vehicle dynamics. Vehicle dynamics is now taking, everybody is now interested in the vehicles now, because there is a very big transition happening in India or across the globe, uh, from gasoline engine to electric vehicle, or maybe autonomous electric vehicles and all that. But the thing is, earlier you will see that there will be only few institute trying to explore this particular topic, but not many of them were quite serious about it. But nowadays you will see that the interest is rising, and with that perspective in mind, through this lecture, I aim to introduce some very fine details, the fundamental details which are required related with the vehicle design. And this is what I'll be talking about. So I'm from IIT Hyderabad, currently an associate professor at Mechanical and Aerospace Engineering. So before we talk about any topic, so of course we need to really look at the important references, and it is important to really go to the correct reference. So first one, that is the Thomas Gillespie. He is considered to be the father of vehicle dynamics, and his book Fundamentals of Vehicle Dynamics has been cited by many, and it was one of them, one of the first that came into being. Then there is another very important book by Ganta and Morello, which is in volume 1 and volume 2, and it contains almost all the details of vehicle dynamics. So starting from the component, in volume 1 you will find the components of the vehicles, and in volume 2 you will see more details about the operation and how to do modeling and all that. So I recommend that those who are quite interested in vehicle dynamics, they should definitely go over this particular book, and this is what I also follow for teaching my students at IIT Hyderabad. And I'm teaching vehicle dynamics at IIT Hyderabad from last 7 years. So and based on that experience, I can say that this is one of the best book available. Then if you just try to go over a little controls and stability, but in short, there's a Dean Carnop book that you can refer. And if you want to just look at the multi-body dynamics of the vehicles, then again Ganta book is there, but not very detailed. You can always look at it and get an idea of how the modeling simulation is being done. If you want to detail, so other than in the vehicle, one of the important component is the tire, and we usually neglect how the tire is designed, how it is working, and how the forces are being transmitted through the tire to the vehicles. And if you want to know more detail about tire, and some suspension suspension related modeling and how to handle this vehicle. So this John Dixon talks about tires in greater detail, and I would recommend that you should go over it. And very recently, this Zazar book, Vehicle Dynamics Theory and Applications, this is a very detailed book, exhaustive book on vehicle dynamics. It has theory, it has applications, it has problems, so for getting the problem in vehicle dynamics, you can refer this. So in between, so like if I say that what 2 or 3 books that you should follow for the vehicle dynamics, I first recommend this one. Okay, then I will recommend this one, and this will always be there. This you can always be refer, because this is the first book that came into being. But these two should mostly encompasses almost everything that appears in vehicle dynamics. And if, so much focus if you want to give on tires, so perhaps serious modeling, so you should look into Daxer. Otherwise these two references are quite sufficient. Now you know that SAE keep on updating their standards, and the standards, that last standard that happened is in 2008, and that is SAE J670. And whenever you try to do any vehicle dynamics problem, or let us say any parameters that are being mentioned, that should follow the standards of SAE. So that is something that you should also know. Now, what are the important softwares that exist, and which one can use for doing vehicle dynamics related study? So one of the most popular software is a car sim that is being used by industry as well as many people. And incidentally, Thomas Gillespie, he founded mechanical simulation company, and which sell this car sim software. So there is a car sim, bike sim, and then there is a suspension sim is there, truck sim is there. So all this softwares are vastly used by many industries, and mostly it was developed by this gentleman who is also called the father of vehicle dynamics. Okay, so I'll be talking a little bit based on this also. We have done some simulation and we will show. Then there's an Adams, which is multi-body dynamics software that you should, one can alternatively, in place of this, if you want to really explore ambiguity of vehicles, you can go ahead with this as well. And so one of the advantages that you can also interface these softwares with MATLAB, and then in the Simulink, and try to do some analysis in coupled mode. Then there are some system modelers, Maple Sim, which is similar to MATLAB Simulink, that many people try to use it. So like it is alternative. System modeler is the alternative of MATLAB Sim, but of course Simulink is far like accepted by many people, and it is also famous. System modeler is also good, but it's all based on like how, whether you want to experience this additional tools or not. And for the 3D modeling, of course, one should look for solid dash, unigraphics, and all that which are available, because vehicle has many components, so it is always better to also learn how to make 3D model of these, so that that can also be used for uh, you can use that as the CAD model, and then based on that you can develop some simulation. So but at the same time, this can also be used for doing FEM simulation in Abacus, right? Abacus, as well as ANSYS uh, for finite element modeling. So these softwares are quite popular among the vehicle dynamics people, and you can take up one and start doing if you're interested in. Now the second thing that I should be referring you, that what are the important labs and the important places from where you should be first getting the information. Of course, in India, ARI Pune is one of the nodal center which like clears, certify all the kind of vehicles. So they are much ahead, and they keep track of all the standards that is being followed across the globe. And they have all the testing facilities so that they can in fact do test and certify things. So we always have to look for their website for any updates as far as the testing and certification is concerned. Now, related with the institute, there are many institutes like the Center for Automotive Research in Stanford, CARS, and then Vehicle Dynamics Control Lab, Berkeley. Then IIT Madras also has Vehicle Dynamics Lab, and then MIT Lab, which is Sloan Automotive Laboratory. And these are the labs basically. You can always try to visit and try to see that what they are doing, and you should try to. You will get an updated information. So that is what basically like we do also, and anybody will do who are curious to know what is going on in the world. And second, like Professor Longoria, who is from University of Texas. I have personally also followed some of his notes on vehicle dynamics, and it was very very great. So some of the example that I'll be discussing also is taken from his notes. Now, these are the labs, but what are the magazines and journals then we generally refer to in vehicle dynamics? So almost all journal of SAE, they are standard. And then individually, we also see the International Journal of Automotive Technology, Springer, and the SAGE publications, which is your Journal of Automobile Engineering, and this one, which is Vehicle System Dynamics, one of the best journal, where you will again find all the updated information. So to refer it, you should visit these journal sites and try to read papers. So that is the information that I wanted to give before I start. Now, before we discuss other details, first of all, we have to really see how do we classify vehicles, right? So generally, you'll see that the vehicles are usually classified based on their size and number of axles. Okay, so here you will see that there are many standards. One is ISO 3833, which classifies ground vehicles in 7 groups. So these are the 7 groups like motorcycles, passenger cars, buses, trucks, agriculture tractors, passenger cars with trailer, truck trailer, and all that, right? And in the passenger car classification, again, you have to decide uh, under what condition those vehicles are called. Like if there are 10 or fewer people, and it is called smaller car if the wheelbase turns out to be less than 2.5. Then a mid-size car, large cars with wheelbase this, or light cars with weight, mid-weight, heavy. So it's in terms of weight, this is in terms of weight, this is in terms of size, this is in terms of passenger, right? So you can see that the type of classification that we do to classify different types of cars. And now with the advent of EV and all that, there are many more standards which are coming. I think those who are interested should try to follow it up in ARAI website. They have come up with many standards, and we should try to follow that. Then there is another standards, which is like Federal Highway Administration, FSWA, based on USA, and these are the classification that they follow. Here I'll not go into much detail of it, but in principle, when we as a buyer look for any car, so this particular classification becomes even more important for us. So, and it is classified based on the number of passengers and the load capacity that it is having. So one is your economy, then compact, intermediate, so all that. You have premier luxury, convertible, minivan, SUV. So that way it goes, and all these numbers classify represent that it belongs to these kind of vehicles. Now, after classification, let us look at what is vehicle dynamics. Before that, I will just show this video that we developed using CarSim. Here you can see, the vehicle is at standstill right now, or in a. So here, what is happening? Uh, there is a normal load you can see, right? So this normal load that you see in the front is more as compared to the rear. Now, the question is why? Because you see that in conventional vehicle you have engine, which is and most of the energy generating or power generating components you will find over here. So that even transmission which is here, so that will also be housed over here. So you obviously you will see that the front portion will always be heavy, and that will make sure that this particular components, normal components in the front wheels are more as compared with this, right? Now, when you start your vehicle, okay, when you start your vehicle, you will see that these components change, right? So now the condition of these normal loads changed from static. When you move from static to dynamic component, so those normal loads are not going to be constant, but they are going to change. Why they are going to change? Because this is one example where your vehicle had cornering effect. Cornering means it is turning. So when it turns, you will see that this portion, this will try to move like this, right? And the whole load will get transferred to this portion of the vehicle, and this portion will have less load because the tire contact will, of course, will the tire will lift. This side will lift, and this side will go back down. So that way, the normal loads of, I would say that the outer portion of, this is the outer portion of your car, will increase as compared to that over here. Now the question is, what is the influence of these normal loads? So here you see that maybe I will first discard this and then show. Yeah. Oh, 1 minute, 1 minute. Yes. So here you see that we have this force which is generated over here, right? What is this force? This is the force which we call as longitudinal force, which is along the tire, right? So this force, we also call it as attractive force. And then you also see there is a force which is not quite clear, but you'll see that there is a force which comes in this direction, that is called lateral force. Okay, so so these are the forces that exist, and all these forces are dependent on the normal quantity which exists. So it means that if the normal uh, uh, at the wheel reduces, it means that these forces will also reduce. Okay, so that is the influence that it will happen, and you can see that as your vehicle is turning, all these forces are oscillating. Here you can see, I think from here this is quite clear. You have here the lateral force, and the maximum lateral force will be applied by this wheel at this particular moment, because this is the one, because this tire is undergoing more deformation, and hence the force which is generated over here will be more as compared to the force at any other wheel, right? So, and these forces are only trying to keep the wheel from slipping. The moment this becomes zero, it means your vehicle will slip outward, right? So we have to relook at these all these forces, and try to see how they vary. Okay, so I'll complete this. Yes. So this is one example. This is what you can see. Just 1 minute. Yes. So now let us look at the vehicle dynamics, how it appears. So it means that what is vehicle dynamics? So vehicle dynamics basically is concerned with the movements of vehicles on a road surface and what are the physical conditions that may encounter, like you may encounter over here. So the vehicle can accelerate, right? You can apply brake, means the acceleration of the vehicle may happen. Then there is a straight line motion happening. So steady state motion, straight line. So you will have a you may be interested in the ride comfort of the uh, comfort in the vehicle. Then cornering and turning, these two are the same thing that is there, right? So before we start discussing about the vehicle dynamics, we need to really understand under what condition we are uh, exploring the vehicle, whether the vehicle is under acceleration or braking or uh, uh, like in the riding condition or straight line motion, steady state motion that it is happening, or longitudinal motion we also call, and or it is uh, undergoing turning, right? So so any one of them you will have to decide, or sometimes you will see that you will have a combination of the motion also, like while you are turning, right, you can also accelerate. So that is the combined acceleration and turning condition that is there. So all these condition, operating condition of the vehicles need to be first defined before you start looking for the modeling of these vehicles. Okay. So what are the dynamic behavior, like what will be the influence of the dynamics of the vehicle itself? So it means that when the vehicle is on move, you have the forces which acts on the tires, okay, which is very very important, and that is the only force that really comes in contact with the outside world, right? Means in contact with the road, and we need to really understand that. And so that, and that keep on changing, as I just explained it through this video. You will see that all the forces, lateral force, vertical force that you are having normal load, then longitudinal force also I explained it to you when we simply started, right? So here, for example, here this is the your longitudinal force that we had uh, over here, right? So all these forces keep on changing when the vehicle is under dynamic condition. Then your gravity, of course, when you are going up, right, over the slope of the road, how the road surface is, whether it is leveled, it is straight, or going up, and how much roughness is there. All that are going to influence uh, like directly these forces, tire forces, because ultimately all the forces that we are going to take, it is going to influence the normal force, and when the normal force get affected, ultimately the tire force also get affected, right? Then when your vehicle is how the wind is blowing, whether it is in the direction of the vehicle or it is opposite to the vehicle or at some angle to the vehicle, right? So it can have different types of effect like drag, it can have lift of the vehicle. Sometimes, let's say if you are going up and the wind is blowing from top to down, then what will happen? You will see that the vehicle will because of the aerodynamic effect, you will have a lift, right? So all these forces are quite important, and sometimes uh, you know the direction of wind also helps to stabilize the vehicle. Okay. So, but it all depends on like how it is blowing. And then we have to, so it means that just to study the whole thing, vehicle dynamics is all about how the vehicle ultimately moves under the influence of these forces when they are accelerating or under braking condition or ride condition or turning condition. Yeah, Manish, you want to ask something? Yes. Okay. So our objective is uh, the vehicle and its components are studied to determine forces produced by these sources at particular maneuver. So these are called maneuver and different conditions. So we will look for how the vehicle responds to these forces, right? Now, to do vehicle modeling, first we have to see whether we are considering the vehicle modeling under isolation, or we are considering the vehicle when it is running on the road, and we have to consider all the control. So when we look at the vehicle under isolation, so first thing that we'll have to look for whether we are separating driver from the disturbances or not. Second, when there are disturbances, we look at the controls, right? And that will help us to reject the disturbances. And also it helps us to minimize, if you are having some small disturbance. So one thing is that either it should reject completely, or it should minimize the amplification of those sources, right? So that's what the control motive is all about, and should look for it. So now looking at the case when your driver is separated from the disturbance and the vehicle is under isolation. So the one of the disturbance that comes up is internally generated disturbance. So which is due to basically engine vibration and the noise that is created. Second, externally generated disturbance. So what we do basically is so these are basically your internally generated are because of the engine vibration and noise. And whenever we try to do the design of the vehicle, we try to do refinement or select the passive dampers or some settings such that uh, like whatever vibration is generated because of the engine and all, this should be minimized to the minimum, right? So that is done with the help of the refinement. Now externally generated disturbances, mostly because of the aerodynamic interactions, crossing winds or wakes, or because of the road undulations. So so we need to consider that while we try to see that. Now what are the forces that we have? So the forces that is there are vertical forces, which are your reactive forces, then longitudinal force, lateral force, right? So these are, so you'll see that all these forces will get affected because of road undulations. And this is what we try to consider, we try to control under the ride analysis of our vehicle, right? And all these are interconnected. So this is what it shows, that all these forces are interconnected, and we need to really consider them together while we try to do modeling. Now in terms of control, what we do, there are two mechanisms: either you control the path of the vehicle, right, or you control the speed of the vehicle. So under this condition, uh, when so what are the objective of that control algorithm that we should follow? One is your stability. The stability of the vehicle should be maintained, agility, fidelity, and linearity. So considering that, we have to do that under the influence of you know these forces that is being generated. And all these forces are directly attached to the tire, and they get affected because of these influence, these effects, right? So any control that we have to design, the path of the vehicle have to maintain the control of the vehicle path. We need to make sure that all these forces are controlled and effects are being taken. And when we talk about handling of the vehicle, we need to discuss about this path control, right? Now we look for the speed control under the influence of uh, performance. If we need to really increase the performance, we try to control the speed. And so these are more or less the motives of vehicle dynamics. So these two things are mostly subjective in nature, and mostly the objective of vehicle dynamics is like handling and the performance. Okay, so so this is how in broad sense we try to divide the different factors in vehicle dynamics. Yeah, so what it shows that stability means it should not uh, like amplify the noise, it should de-amplify the noise. Agility means sensitivity, so it should be sensitive enough to capture the changes that is happening because of these disturbances, and the control should be accurate, and then it should also be linear, so that you get whatever the vehicle wants to have the correct path, right? Now, after this modeling, mostly we try to do the testing of the vehicles and even the tire testing. So, what are the tools which are available? So, one of course, the most conventional tools to do the testing is you have lot of accelerometers, right? You just put accelerometer all over, and then you try to do testing, isn't it? And then from there you do modal analysis and try to generate the mode shape of all these vehicles, and then you know that which component is basically having what frequency and what mode shape, and you try to reject some of the mode shape, so that when the vehicle is on move you don't get you know uh, the disturbance from those components, because they may start oscillating, right? For example, let us say you have a vehicle design, and this is like more or less your frequency mode of first frequency of this whole like car body. Now when you are putting the door, it may happen that there is another frequency which comes over here, right? When you are putting the wheel, it may happen that another frequency come over here, right? So as you increase the mirror and all that, there are many more components in vehicles, and you'll see that they will have different frequencies. It is required that most of the frequencies should, although it's not in our control, but it is always required that for a given speed, when we try to move over the road, it may happen that all of them should not come closer, otherwise everything will start vibrating together, right? And it should be away uh, from the riding comfort of our vehicle. So there are different mechanisms through which we can damp out these vibrations. So of course, using the passive kind of dampers, active dampers, semi-active dampers, and all that. Nowadays, many people are thinking of using active dampers. So so that we can damp those vibrations. The first purpose, whenever we try to design a vehicle, so it is always important to really know what is the frequency of that. Okay, so as I said, one way is to use contact based measurement using accelerometer, and another method is the laser based non-destructive type of measurement. So this you can see the laser vibrometer, scanning laser vibrometer from Polytech. So it generally has these heads. Okay, these are called scanning heads. So with the help of these three heads, you can do 3D measurement of any kind of structures. If you're having one set from here, another set from here, with the help of this you can just scan it over everywhere, and then you can have the complete vehicle testing, complete testing solution of the vehicle altogether. Okay, so that is something that many people are trying to establish and try to see it, so that we get the accuracy of these modes as well as and the important thing is that you can also generate the mode shape altogether. Okay, so that is very important. So so how you do it? What you do is you put this system on the shaker. This is your shaker. You try to excite the tires, right? And when the tires are being wheels are being excited, all this system will go into the vibration, and with the help of this scanning head you can do the measurement, right? So this is your laser based measurement. We do have one system with us, and we have just one head. So with the help of this you can do, let us say, if you want to do measurement over one side of the vehicle, right? So that you can do the measurement with one single head. Okay, if you want to do 3D the complete, you really need, at least three head of this, and then you can try to do the measurement. And with the head, and this is how basically it looks like. You have the processing unit, and then this is the head, and you will see that the laser basically moves when you define the reason. Okay, so this is another example. This is my group. So this is an example, right? Measurement of the wheel also, so that you know what is the frequency of the wheel. You can define the reason, because with the help of laser, you can't really do measurement over black portion, right? Because the reflectivity is quite less. So in that particular case, you define the reason. You can do some spray, and then the laser will come and do scanning over all the surfaces, and you can, meanwhile you can put here the shaker, it will excite it, right? uh, at the same time, if you want to do, the side measurement where the laser is not able to reach because you have single head, you can put here the accelerometers on the side and try to do the combined measurement, right? So this is how basically the world is moving, corporate is moving, and they are just trying to go over, like, in shortest possible time, how they can do the like frequency related measurement. Another very important, like measurement in vehicle is the tire forces, as I said. For that, there is an equipment called TechScan tire TechScan tire imprint system. Okay, so as MTS, right? MTS, you do some fatigue testing and dynamic testing. There also you can, like this, you can apply the loading from this direction, sinusoidal, and then you can measure how much load is being transferred. So that is one set of measurement where you can do a lot of changes. So like this here you can see, maybe I'll just move this. Here you can see, this is kind of measurements. The wheel is being placed here. Here is a drum. So drum will move, right? Drum will move, and you can measure the tire forces or the contact measurement at this location. So this is one set of experiment where you can do static dynamic testing. And this system is quite handy. This one that I was talking about, which is a tax scan tire scan system. So you can just drive your vehicle on the top of it. Okay, you can go here, you can see the mark, the vehicle. In this vehicle we tried to test. So here the vehicle will move on. The moment it goes over it, it will give you the tread information and the pressure, contact pressure over there. So after you get the contact pressure, what you really get, the area over which the contact of the tire for a given pressure that you get, right? So based on the pressure, you will see that the contact will also change. Now the based on that, as the contact changes, you will have the normal force that is being generated, and based on the normal force you will be able to find what is the longitudinal force that is being created. Now you can also keep your tire here and turn it, right? When you turn, you will get your wheel, which will be something like this, right? The contact region will be something like this. So you can find out these angles also, right? These areas, that angles, all that you can in fact capture, and that is very interesting to see lively when you try to do these measurements. So second thing, let us say, second information that we really require is the temperature. Nowadays the thermal information of the tire has become quite essential, because we are having very good road thanks to, like multiple highways that are coming up, and we don't have any control over the speed. Everybody starting from small guys who is trying to learn vehicle or car to uh, the experienced people, they are driving the car. But what we don't really care most of the time is we don't know how our tire is, right? So you will see 90% of the people don't really care about what is the condition of their tire unless the tire gets burst, right? So all this happens when we drive at a high speed. You have a temperature rise that is there, and if wear and tear of tire, so as to an extent that you can't really control its rupture, and this is where the tire burst phenomena happens. So we need to really uh, lively track the condition of the tire, and there are many tire companies which are coming up with smart tires with where they can provide the information of the contact, they can provide the information of the tire thickness, they can provide the information of, anyway, pressure is already there, that is a tire pressure measurement unit for quite some time, but they are inserting strains in the tires so that they can know how much stress is being generated in the tire. And so it's just to know live information of the tire condition, so that uh, so because we are heading towards autonomous, so not just view field or other things are required, but the safety lies mostly on the tires, right? So because that has been, of course, if it is new you don't really care, but as it become age, then you need to really look at all this information. So we have this the IR thermal camera, right? And that can be used, one minute, that can be used to find out this temperature profile over a region of a tire. Let's say when it is when you are running it for, let us say, for 2 hours, 3 hours, come back and see how the temperature profile of this tire over the surface. Okay, so there are two things that one can measure. One is the pressure profile, another one is your thermal profile of the tire, and these two informations are quite important in understanding the condition of the tire. Of course, it will also change the forces which are generated at the tire and road interface. Okay, so these are all about how we do testing of vehicles and the tires. Of course, there are many more individual test setups which will help you to test I guess you will find them in many labs and all, and you can explore that. But more or less, like how you do it for a whole vehicle, how you do it on the tire, these two things are quite important. That's what I tried to cover over here. So before we start going into the details of even more vehicle dynamics, one should really look for understanding. When we are teaching to our students, they can't really get an idea of vehicle unless they start making some CAD modeling of that, because getting some information of like how it really works, all this. So at the end of the course, modeling and fundamentals that our student understand, they should also be well versed in making the CAD of these, and all these most of these CAD models are available at many websites, but uh, our own students have created them in the class. It's like informations are available, but unless they create it in the class like as an assignment, so they are not really going to understand more and appreciate it more. So that is something that we should also do, and it is in vehicle dynamics, it becomes an essential part of learning, right? Okay, so when we do vehicle dynamics, when we need to write So it means to understand the dynamics, we need to look at important components and write equations for them, right? So here you see that there is a master vehicle dynamics equation, okay, and this has to be interfaced with all the component that you are having. And what are those components? The components are, let us say, start with tire, right? So here you see that the tire models all depends on how the road condition is, right? So those database needs to be provided. So if from the village, you should be providing one database of mud road, database of highways, national highways, state highways, and all that. So based on that, you will be able to get the tire forces that will be generated over here. So that is another block that is essential to interface with master vehicle dynamics equations. After that, coming to drivetrains, so how the power get transmitted from engine to the wheel, and finally this have to be interfaced, right, with again master equation. So that particular thing we call as drivetrain models. Then aerodynamic loads, so based on the wind condition and how the vehicle is moving up, down, plane, it's rolling on the level road, we need to look at we need to consider that also in the vehicle dynamics. This is a very important component, and sometimes it is helpful in providing stability to the vehicle. But mostly, it will always, air drag will always reduce the mileage that we know. And of course, we need to really look for, we need to know how that can be overcome, and how to increase the mileage in that sense of it. So the shape of the vehicle, so we need to work on the optimization of the shape of the vehicle such that we can increase the mileage and the drag is reduces, right? Then there are many assembly models of the vehicle body itself that needs to be considered. Then steering, right? Now what kind of steering you are having? Now whether you are having a straight line or cornering effect, based on that you need to consider it. Now under what condition your vehicle is moving, whether it is under neutral steering, whether it is under steered condition or over steered condition, right? So we need to look at the correct steering conditions of your vehicle, and provide an input to our vehicle model such that we know whether vehicle is under straight line or longitudinal, sorry, straight line motion, or it is cornering motion, something like this, right? Now to do ride comfort analysis, this particular block is very, very important, which is your shock or spring and kinematic model. So suspension model basically. So there are different kinds of models that we know. One is called like quarter one degree of freedom quarter car model, right? Second is your 2 degrees of freedom quarter car model, 3 degrees of freedom quarter car model. So now just to explain it, so let us say if you are having a vehicle here, right, and there is a spring, there is a damper, right, and then you are having a wheel, right? So now if I consider the wheel as rigid, right, so you have just this mass and the road is there, right? So this one is the single mass, right? So that's why we call it as 1 degree of freedom quarter car model. So if I just try to, have a car which is something like this, right? I'm sorry, I'm not able to make it properly, but so let us say this is a 3D diagram of the wheel, and so you have a suspension here, right? Then here also, here also, and here also, right? So if you are dealing with this car and you have four wheels, right? Now, under what condition you are considering this vehicle? Let us, if you are just dealing with the vertical motion of this vehicle, right? In that case, it doesn't really make sense to use all the four wheels and do the analysis. So in that case, one can simply focus on one quarter of the car, right? So that way we call this model as quarter car model. Now, if let us say if you have a motion which is like this, right? So here you see that these two components are having same kind of motion and these two components are having same kind of motion. So it means that we can just have one equivalent from the rear, another equivalent from the front. It means we can have two, one from the front, another from the rear, and form half car model, right? So this is your quarter car model, which is essentially valid for upward downward motion that you come across. And if there is some kind of pitching happening, right? So in that particular case, we look for half car model. If let us say you want to deal with all the motion, for example, a vertical motion you want to deal with, you want to deal with rolling, you want to deal with pitching. Okay, so in that particular case you have to go for full car model, right? So that way all this terminology came. You have quarter car model, right? Half car model, then full car model. And for each, so this is your full car model, right, where all these dampers are being provided over here and connected with the wheel, and each one of them can be 1 degree of freedom, where you deal your wheel as let us say rigid, and only the car body will be considered as the moving body, right? And so this is 1 degree of freedom. But if you just try to divide this into two parts, where you have one mass, and then you consider another mass over here, which is like some portion, some brackets that is near just below the suspension. Okay, so here you have suspension system, then you have the auxiliary masses which comes up, and after that only the tire comes up, right? So the wheel comes up over here. So if you are having this mass and this mass, we can call it as a 1 m and 2. So we define such kind of model as 2 degree of freedom quarter car model, right? And if you also consider the mass of the tire, so in that case what will happen? You will have one mass, two mass, three mass. It means that 3 degree of freedom quarter car model. There may be if you want to increase these degrees of freedom, and so you can divide this tire into multiple spring mass element, right? And that way you can increase it from 3 to 4 to 5 to 10, whatever degrees of freedom that you want. But then you will have to go for minute lumped model of these tires corresponding to different mode shape, corresponding to different modes of the tire. And why it is essential? It is essential because uh, it is essential because like you need to really find out, there will be some modes of the tire which will generate noise, right? It will generate some kind of vibration, and that will get transferred to your upper structure, and disturbances either in terms of vibration or in terms of noise. You have to go to that level of degrees of freedom, right? So and then consequently you can just get the same modeling for all the four wheels and then do the analysis. So this is where one had to be again clear what is the frequency range where we are looking for to analyze our vehicle. Okay, so if it is low frequency vibration up and downward, very simple model one can select. If it is higher frequency, very high frequency, you go for 1 or 2 degree or higher degree of freedom model of the tire, such that you can capture those vibrations. Okay, that is very important concept. So it means that to develop the complete vehicle dynamics model, you need, of course, you have brake model based on what kind of brake you are using, drum brake, disc brake, and all that. So you will have to use those uh, like uh, uh, like models over here, interface it with your vehicle, complete vehicle model. So that forms the very standard blocks which are there in a vehicle, and based on that only one needs to look for the accurate modeling. Of course, now in terms of the modeling, there are a lot of things that we look for, whether you are doing steady state analysis, whether you are doing okay. So whether it is the connected vehicles where with the trailer and all, so all this we need to really look for whenever we try to do this modeling. Okay. Now, so the one thing that we need to really understand, how to represent a vehicle. Many people just like uh, they forget to know like how to represent a vehicle properly. So first of all, one can also first see whether you are going for one mass approximation vehicle. If it is just longitudinal kind of motion that you are trying to deal with, where the tire influence are not really required, so we can just take one mass approximation. Where we are doing some acceleration analysis, we are doing cornering analysis, right? So in that case one cannot, but when we do comfort analysis, then we need to go for these uh, two masses or higher masses approximation. Okay. So how we do it? So that's what I was saying. For acceleration, braking and turning, one can always consider a vehicle with one mass approximation, where the mass is located at the CG of the vehicle. Okay. And for ride analysis, for comfort analysis, the wheels are treated as separate, or the brackets or your like chassis, and some connectors also come between suspension system and the wheel. So that can also be treated as a mass, which can generate some vibration. Okay, so that way you can go into two, and the tire as third degrees of freedom. But in simple form, we don't go into those details. So we say that we can start with the two mass approximation, one for the wheel, sorry, car body, and another for the wheel, right? So how do we do it? So always, body, car body, the upper part of the body, right? The upper body that you get, this one, this will always be, because of suspension and all that will always be down, right? And that's why we call this one as a sprung mass. So we call it as a sprung mass. And this is called unsprung mass. Okay. So spring is here, suspension is here. So that's how basically we define the sprung mass and unsprung mass of the vehicle. So here body mass is considered as sprung mass, wheel mass is considered as unsprung mass, and as far as the degree of freedom of the vehicle is concerned, for one mass approximation that we take, so these are the one. It contains translatory motion, right? Translatory plus rotatory motion. So translatory motion is your longitudinal force, which is along the body of your vehicle. Then on the side one, you are having lateral motion, and then you are having vertical motion, which we also call as downward motion, right? Downward motion. Now, the rotation is also associated, because this is a rigid body, right? This is a rigid body, so we need to consider rotation as well. So along x-axis your vehicle rotates, we call it as a rolling of the vehicle. Okay. And when it does along y-axis like this one go up, this one goes down, like this, when you are having, so this is called pitching. And along this direction that you are having, this is called yaw angle, right? So these are 6 degrees of freedom: longitudinal, lateral, vertical, they are translatory motion. Then roll, pitch, and yaw, they are rotatory motion. And whenever we try to write down the equation of motion of full car body, we need to find out all these, right? All these situations. So rolling, pitching, yawing, and like all 6 degrees of freedom. Now, the other form that we come across, we will be talking about this one a little later. Uh, yeah. So this is here such kind of coordinates where the coordinate is fixed to your body is called body fixed coordinate system. And there is another coordinate if we want to analyze our vehicle with respect to some earth fixed coordinate, right? So here this one is not fixed to the body. So there are two coordinate system that we deal. One is body fixed coordinate and earth fixed coordinate system while we write down the equation of motion of the vehicle. Okay. So this is what these are the degrees of freedom under different components. So body fixed coordinates. In body fixed coordinate, you have forward, lateral, downward, roll, pitch, yaw. And in earth fixed coordinate, we have forward travel, travel to right, vertical travel, heading, course, side. All this will come into picture. Then other than the vehicle, what we should also look for is the coordinate system of the wheel, right? Because the wheel tires will be having forces and movement generated over it. So for example, let us say you have the tire which is tilted over here, right? And it is in this particular plane. Okay, so this is the wheel plane that you are having, which is tilted from the normal one by an angle. Okay, which this is your inclination angle that you are having, right? And then it is heading towards. So this wheel is heading towards this direction, right? So this is your alpha, which is called as the slip angle, right? And based on that, let us try to understand what are those degrees of freedom associated with it. Okay, so here you see that the wheel is in this particular plane. Okay, the wheel is in this particular plane. One minute, yeah, yeah. So in this particular plane, and this is your inclination angle, and this terminal force, right, in the direction of the wheel, right, in the direction of instantaneous direction of the wheel, I would say. So here your longitudinal force will be generated uh, along the wheel plane, right? Then you have lateral forces which are generated over here, right? This is called lateral force, and normal force which will be generated over here. So three forces are very important in the tire which will control the vehicle. First one is your longitudinal force, lateral force, and normal force. So lateral force and longitudinal force are dependent on normal force. Okay, so normal force will of course varies how the wheel is tilted and how the vehicle is moving, on which side of said when the animation of the wheel when it was tilted, that side you will remember that the normal force was changing continuously. So because these two forces are directly proportional to this, hence these two also will vary. Now, as far as the rotation is concerned, what is really happening? You have here, first of all, the wheel torque which is coming, and we call this as the rolling moment of the wheel, right? So the moment which acts about the plane or about the axis which is directly proportional perpendicular to the wheel, so that gives you the rolling moment. And there is also one which just tries to turn the wheel, we call it as overturning movement. And there is the third one which is this, which we call as the aligning movement, which is very important. We also call it as cornering movement. Okay, so cornering movement was just act like this, it tries to tilt, wheel is like this. Okay, So it will try to tilt the wheel, is called your aligning movement. Why it is called aligning movement? Because if the tire tilts to some other direction, this will try to bring the tire to its initial position. Okay, so that's why it is called aligning movement. So you are having overturning movement, you are having rolling movement, you are having aligning movement, related rotatory component of your wheel, and then forces, translatory components are longitudinal, lateral, and a normal force. Okay, so these are the component, and in this case alpha, which we call as the slip angle, is one of the important factor in the tire forces, and this aligning movement and lateral forces are function of this. Okay, so these are the important components in tire coordinates, and that, so now the question is, we have the forces in the car body and the forces in the tire, and they need to be coupled together, right? So yeah, now there is another important concept that you should be knowing, that there is a single track model and a double track model of a vehicle. Now in the single track model, what really happens, we consider a vehicle, so we consider both these two vehicle as same, right? The front one will be something like this. Let's say you are having a vehicle, so I will say that these two rear wheels are considered as one. Okay, and let us say the front one is considered as same. Okay, so in that case what really happens, I'm representing this as only two wheels, right? One is rear, this is your rear wheel equivalent wheels, and here it will form the front one, front wheel, right? Now what is this angle? This is your delta, right? Delta is the steering angle that you are mentioning. So when you try to turn your vehicle from the front, so front steered vehicle, so your vehicle will turn in this direction. So that way, so what is happening here, we are representing this vehicle with only two, and it is like a bicycle, right? So we call it a bicycle model, or we also call it as single track model. Now let us say if all the four wheels are, or these two wheels are having different deltas, right? And all of them are monitored, or they are steered. So it means that you may have to go for all four wheels, and in that case we call it as single track model. So here you are having all the four wheels, and we try to find out the condition, like we try to, first of all, there are two things, like we have to first get the forces which will act along the wheel and perpendicular to the wheel. So this is your longitudinal force, this is your lateral force, right, for all of them. Then you also need to find out what is the instantaneous velocity of each wheel. So let us say this is your v1, this is your v2, this is your v3, this is your v4, and you see that all the four wheels are moving in different direction, right? So based on that, we try to find out another component which we call as your slip angle, of course, one, and another one is uh, like as based on the velocity, we also try to find out slip ratio, which will help us to find out the longitudinal force, and the slip angle help us to find out uh, your lateral forces, and also cornering moment. So that I didn't mention over here, but in the previous slide I was mentioning. So that's what we do. So after you put all these forces over here, right, what you do, like when you turn the vehicle, you get centrifugal force, right? Centrifugal force will be developed over here, mv square by r of this kind. So if velocity v is there, so you will have mv square, and what is your r will be from this to this. Okay, so in the influence of lateral force, longitudinal force, this force, we try to understand what will be the turn of your vehicle, right? what would be the turn of the vehicle, how the vehicle will turn. So that cornering motion of the vehicle needs to be understood based on either single track model. Okay, this is called single track model, or this is double track model. Okay, so this kind of abilities are required for cornering motion. Like how to choose, like which one to use. One is, let us say if your vehicle is having like the front axle, which is here, right, and rear axle here. So you can just see that this, if we call it as B and we'll call this one as L, right? So of course, if L is very, very greater than B, you will see that this and this will act similarly, right? And this will act similarly. So that way we can just say that the equivalent, I will just bring here the equivalent effect over here and equivalent effect over here, and try to analyze my vehicle only like a 1D effect, like a bicycle model. This is single track model. Okay, so long vehicles can be represented quite easily with the bicycle model or single track model, and that's how basically you will have to decide. Let us say if you are having multi axle, so what you are going to do? If you are having multi axle, you are going to have another wheel over here, right? So their multi-axle vehicles can also be analyzed. Their turning, their cornering effects can also be analyzed using all these models, right? So we should first, before doing any analysis, it is very important that we should know how to really draw all this vehicle dynamics model. After that, the forces, right? You have the forces. Important forces are you have here the force through which the trolley is connected, right? Then you have here air drag force. This is your aerodynamic force, air drag effect, which is acting at, let us say, at a distance h from this. And of course, it will depend on what is the centroid of this frontal area, right? This is your frontal area, isn't it? So this one, the wind will also be acting as the CG centroid of this frontal area, which will depend from this actual CG of your body. And this is your acceleration, right? And this is your velocity, which is acting, and because of the slope, it will push you downward like this, and along the body like this. And because based on this component that you are having, that will decide how much is your tractive force which is acting over here. So these are all called your tractive forces, or braking force. If you are having braking condition, it is called braking force. If you have tractive condition, acceleration, it is called tractive forces. And these are the forces which we also call it as longitudinal force. Okay, these are longitudinal force. So that I was talking about, that develops in the tire. So these are the forces that you have to use. Now there may be rolling forces, so that may be a little different, and so that also needs to be considered. So after you consider all the tire forces, dynamic forces, trolley force that you are having over here, and then weight, you are ready to write the equation of motion along and vertical direction, right? And also you can write the moment about one of the wheel. So the one motive that we are having is, we have to first find out the normal loads at the front and the rear wheels, and after that only you can find this and this, right? So how it appears, so let us see. So to write a complete equation of motion of the rigid body like a vehicle, here let us assume that your body fixed coordinate is having rotation, which is omega, and here you are having a small omega, where one of the component of this body is called the center of gravity, of course. And this is your earth fixed coordinate, right? And this is your body fixed coordinate. This is small one is body fixed coordinate. And then you will have to write the equation of motion. So here you are having six component velocities along vx, vy, vz, all in the body fixed coordinate, right? This is x, small y, small z, and then rotation, which is omega x, omega y, omega z. So use either momentum or regular momentum both this, right? So here for will have to use this and then apply the Newton's law. The important to have this external forces coming into picture, you have to write the rate of change of this linear momentum with respect to earth
Hello. Hello. Pandey sir, your voice is not
is
audible.
the quantity which is defined this. Oh, is it?
Hello.
Hello? Hello?
Your voice is not audible. Breaking of
Oh, is
voice.
it? Okay, 1 minute. Uh, is it okay?
Yes, sir.
Okay, I'm sorry. There may be a little bit of internet problem because of that. It is happening. So please stop me if it is not, if there is a problem. Okay, so based on that, you see that we have like when we write down this particular equation with respect to earth fixed coordinate, then what will happen? We can write it like this: the rate of change of, this, the rate of, there is a formula where we say that the rate of change of the quantity which is expressed in local coordinate, right? So if you try to find the rate of change of that quantity which is expressed in local coordinate with respect to global coordinate, okay, I'll write this. This is local, this is global, okay, is equal to rate of change of this local quantity with respect to local plus omega cross p, right? So that local coordinate is moving with respect to this angular velocity. So if you write that, you will be able to capture things properly. And F is your force, which are the external forces. So directly you don't have to, so this is your Newton's law, and since all the components are expressed in body fixed coordinate in vehicle, so we have to use this particular formula to write the equation of motion, and this will turn out to with this. So this is your translatory equation of motion, right? And similar to that, one can also write rotatory equation of motion for rotation along x and y and z. So in place of your linear momentum, you look for, yeah, in place of linear momentum, what you are looking for uh, uh, is the rate of angular momentum, which is given by your h, right? So this way we can write 6 degree of freedom equation of motion. And here, let us say, let's take an example here. You know, this is your vehicle, right? And usually we have 6 degree of freedom system for a vehicle. So since this is, there is a straight line motion which is happening like this, so how to reduce it to 1 degree of freedom model? So in this case, when we assume that your vehicle CG is here located at h distance from the road, and also from rear wheel it is at a distance L2, and from front one it is at distance L1. So you can do these FBDs, right? You can have WR, which is your normal load, and mu times WR, and here it is WF. So assuming that this is rear wheel drive, okay, so when we assume that is a rear wheel drive, wheel drive. So in this case, we have to consider this. So this is your force, tractive force that is will develop over here, mu times WR. And under this, and since it is not front wheel drive, so we don't have this component, which we are writing as mu times WF, right? This is not there because here rear wheel drive is being considered. If it is front wheel drive, you have to consider this. If it is all wheel drive, you have to consider both, right? So that's how basically we need to do it. Now we will write the equation of motion. So first of all, for like condition, since it is straight line motion, we can very easily assume that there is no pitching, there is no roll, there is no yaw. Under that condition, all these angular motion will get cancelled, right? All of them will get cancelled, and you will come across only this is equal to fx, f is equal to y, and this is equal to z, and based on that this equation can be written. So here you have, this is vertical is z and this is x, so we just need to use these two. So by doing that we can write down. Similar to that, for rotatory motion also you can just cancel all the component, and the rotation can happen at the max along the y direction. That's why you see that only this equation is retained. So it means that to write the equation of this body in the plane, you just need 1, 2 and 3 equations, and with the help of that you can interconnect all the variables which are appearing. So from here you get the relationship of the axial loads, right? And from here you can just take moment about CG. So if you just try to use this and this, so you will be able to find out your WF and WR. So after finding WR and WF, you can use them to write the equation of motion using this, right? So this will give you like sorry, using this you can write equation of motion, because fx is equal to max, right? So this is what it will give. So because all other components are now computed, all this wf is computed, wr is computed. To find fx, you simply have to do mu times wr. Since wr is computed, you can substitute it over here. That will give you fx, and then fx is equal to max or mx double dot, right? And then you can integrate it to find out just acceleration you can find out, or velocity or displacement, whatever you want. So that's how basically we try to do it. And this again the same thing. I'll, yeah. Now the another important component is the tire, that I discussed about writing the equation for a vehicle. So what tires basically consist of? So a tire basically consists of rubber, series of synthetic materials, and we have to first heat them together to form some like engineering product, right? So the main components are fiber, textile, steel cords. They are the main component of tires inner liner, body plies, beads, belts, sidewalls, and tread. Okay, so that's how basically you decide them. Now let me explain it with respect to this section. So this is what is called your bead, and you have the steel wires which are plugged over here. And then you have the carcass, they are the body plies, and there are also some which is like wrapped over here to control the motion of, or control the deflection of this layer, so that it doesn't really go out. So you can see that there are some sidewalls which are provided, which will prevent them from going sideways, right? So they are called body plies, right? And then we have some kind of layers, inner layers that we put here, you can just see. And then on the top you are having the cap. Okay, now there are two types of tires. One is called radial tire, another one is called non-radial tires. Okay, in radial tires we put these plies in the circumference direction. Means from here you wrap and then put it like this. Okay, so you can see that all of them are wrapped like this. While in non-radial, you do it at a cross angle. Okay, like this, like this, like this. So these plies are arranged in the cross direction like this, right? So now what is the difference? So let us say if you are turning your vehicle, right? So under that effect, you will see that the radial tire contact will remain intact with the surface, but in non-radial surface, you can see that the sideways will lift. When the sideways lift, you have here the small contact area. It means the forces will be less, right? So that's what the difference between these two. So and the more component that you can find are these that you come across. I'll not go into detail. Now the another important thing, how the tires are specified. This is again very important thing before you can go ahead. So the tire is classified like this. So here you can see this is called your tire print width, right? These are the side walls here, and this is your tire section. Okay, this is your pan width and this is your total section width of the tire. So width, section height, print. So and of course the dia, right, the diameter of your vehicle of your tire. So that is important. So now let us try to look at these different components. So this is one component. So that is called your how much like what is the tire width. So this you can see that your this component which will help us to give this tire width in mm. Okay, then what you get is, so what is this tire width? This is the width that we are talking about. Okay, then what is provided? You provide here the ratio which we call as aspect ratio. Okay, and that is provided in the percentage wise. So if your width is given, then you can find out the sectional height from this aspect ratio. Okay, then this component says what kind of tire. So basically from these two data you can know what is the width of the tire and what is the height of the tire. Okay, then from here sorry, this will tell the radial. Then this will tell what is the diameter, rim diameter, what is the diameter of this rim over which the tire is going to go over. Okay, so that also tells. Then you have loading factor, right, loading rating, which is your 96. So that tells us what is the maximum pressure that it can take, right? And h, this tells about the speed rating. So it means that based on this rating, for example h, if you go to h rating, it will tell that you can go a maximum of 210 kilometer per hour with this tire. So it means that you can't really use the tire which is being used in uh, like bikes, in some four wheelers, because and also because it has the pressure. So one is the load requirement, another one is the speed rating. Okay, so all the tires have this specific factors, and so one has to be very careful when we are using some other tires for our purpose. Okay, so these are now let us look at how this forces are being generated. As I said, so this is your wheel, right, and you have this longitudinal forces. This is your overturning moment. Then this is your vertical forces, and this is your this is your aligning torque, and this is your rolling moment, and this is your lateral forces, right? And the angle between this and tilt is called the camber angle of your wheel. So for example, let us say from the vertical the tire, if you just look from the side of the front of the tire, so the angle that comes up over here is called camber angle. Camber angle is very, very important influence. So For some of the vehicle, we tilt the wheel outward, right? So the forces that you're going to find, that also needs to consider this camber effect. When you try to see the tire from the top, you see that in the front portion you have this angle which we call as the slip angle. Okay, so this here, this one is when you look from this direction. Okay, this you come across when you look from the top. Okay, so this is called slip angle, and slip angle basically defines what would be the lateral forces and what is the aligning torque. So in principle you have longitudinal force, normal force, lateral force, rolling movement, pitch movement, and you have yaw movement. But we have all these is called in as a overturning movement, rolling resistance, and aligning movement in the tire coordinate space. Okay. So what? So how these forces are generated? So when we talk about the vertical deflection, right? So the normal force that you get, that is associated with the vertical deflection. So Fz is equal to kz into delta z, and k will give you, so k will give you the coefficient, spring stiffness coefficient corresponding to that. And what is that force called? Rolling resistance, right? Similarly, you have longitudinal, which will give you this Fx, means x direction force. So this is your Fx, right? Is moving in this direction. So you have your Kx times delta x. And then lateral force, in lateral force is like this, right? On the this side. So that is called your lateral force. And in principle you will see that this kx is always greater than, means longitudinal deflection is stiffness is more as compared to vertical and then lateral, right? So how do you explain this lateral effect? Through this particular picture I would just like to explain. So here you see, when you try to turn your vehicle, what is happening is you are when you turn your vehicle, the lower portion of the wheel gets deflected. This will go outward and this will remain at the road. So what will happen? Lower portion will deflect. So because this tire is made of rubber, right, and it has elastic property, so it will try to bring this back. Okay, the force which tries to bring it back is called the lateral force. Okay, so from the top, if you just try to this is how basically it happens. Okay, so this is what is called lateral force. Now over the contact region, so this is, let us say, your contact region. Now when you try to find the total force, and it happens that it is not passing through the centroid, right? It is not passing through the centroid of your contact area. In that case, there will be some trailing movement arm, and the force, the movement which is generated from this shift is called cornering movement. Okay, so that's what I was talking about. So there are three forces in the tires which are important: longitudinal, lateral, and cornering movement because of the lateral forces. Okay, so these are the things, and this is your this is how basically rolling component varies. So let us say if the rolling force is equal to mu r times fz, so again it is a function of normal load. So here you can see that uh, it varies like this. So as you increase the speed of your vehicle, what really what happens? Your resistance increases, right? And after some time, which we call as the critical speed, it increases exponentially. Initially it is linear, let us say, approximately, and then it increases exponentially. So this speed we call as critical speed. And what really happens, if you might have driven your bike, right? So when it crosses some speed, you will see that the front wheel start oscillating, right? Wobbling of the wheel starts happening, and that is precisely because of these effects that happens at the higher speed. Okay, and longitudinal forces, how it varies? So to find the longitudinal forces, we need to find out basically so what really happens, let me first explain. So when you turn your wheel, your uh, let's say the vehicle is moving at some speed. So when you apply your accelerator, what happens? You are trying to increase the speed of the wheel. So since this is in contact, so this portion will become compressed, right? Compressed, this portion will become expanded, right? So because of that, the speed of your wheel slows down at this location, okay, at the contact region. So the speed at the contact is different from the speed over here, okay. So there is a difference in the speed, and that difference in the speed leads to that we call as the slip ratio. This is what this is called, slip ratio, okay. So you'll see that because of this slip ratio, this longitudinal forces develops. So as you increase this as the speed of your vehicle increases, slip ratio increases, and longitudinal force also increases to a point. After this, it will start reducing, and if you increase the speed more, your wheel will start sliding, right? So that is called sliding moment. So this is your acceleration. This case is braking condition. Okay, so when you apply your brake, what again, when your vehicle is moving, when you apply your brake, it means the movement is this direction. But when you apply your brake, you are restricting the motion of wheel. It means you are applying your torque in the opposite direction. You are slowing down the vehicle. It means that in that case, what will happen? This portion will be extended, right? And this portion will be compressed. So opposite effect is happening. That's why you have negative slip, okay. And it will have almost the same behavior. And in this case, what happens, that you will have a complete locking of the wheel, and the wheel will slide, okay. And here the wheel slide by rotating, by rotation, right? Here the wheel slides by getting wheel lock, and that's how longitudinal forces vary. So we always work in this direction, in up to the peak to peak we try to work for the stability of the vehicle, okay. Similarly, you have your lateral forces that can also be written like this, which is Fy is equal to cornering stiffness into slip angle, which is your alpha, and this is your movement, right? Aligning movement that I was talking about. So, so that's how basically it is being divided. So with this example, I will just finish it. So let us take a case where you are having longitudinal motion, okay, and your vehicle is moving in this direction. So we can divide the two components of divide into two components. One is your vehicle, another one is tire. So in vehicle, what are the forces which are acting? One is your longitudinal force, which is acting from here, like which we call as traction force, and the opposite direction there is a wind drag, which is acting over here, right? And as far as our tire is concerned, so we have our in like this is called acceleration or engine torque, which is trying to move your wheel. This is a braking torque, right? And then you can have some losses, viscous losses related with your uh, uh, viscous losses which is generated in the wheel, right? So that equivalent version of this force can be found at the contact, and this is your tractive force, which is same as this, but this is per wheel. This is for one wheel, and here you will have to write it for all the wheels, right, when you deal with your whole vehicle. So in this case, these are the forces that we need to consider. So let us write down first of all the variables. So here v is the variable which is your vehicle velocity, and this omega w is the rotation of this wheel, which is another variable, right? So for vehicle motion, we can write down this equation. So mv dot is equal to this nw. Nw is what? Nw is the number of driving wheels. Okay, like if let us say it is front wheel drive or rear wheel drive, you need to really consider only that many wheels. For if it is front wheel, NW is 2, right? Front rear wheel, both the rear wheel, NW is 2. All wheel drive, NW is 4. So that way you will have to consider, and the tractive force which is developed for each wheel, that has to be multiplied, and then the drag force that you are having. After that you can write down this equation. And for the wheel, again, this is your engine torque, this is your braking torque, so difference you can take, sorry, yeah, so difference you can take. Then the moment because of this tractive force and the losses that you can write. So basically, since the wheel is rotating, you have JW is equal to omega wheel dot is equal to all the moment or the torque that you get it, right? So uh, they are the like these quantities are the moment, effective moment that is acting uh, at the centroid of the wheel, right, about which you are writing this equation. So after you write both the equations, I what you need to do, you need to linearize them, right? Whenever we have a set of equations like this, non-linear equation, they are all non-linear, right? Fv will be directly proportional to v square. This is all non-linear. So what we do, we have to first linearize them. That will give you Jacobian x, right? And then we try to find out uh, eigenvalue of Jacobian, right? Now eigenvalue of Jacobian when we'll find, and if the real part of these lambdas, this real part of lambdas turns out to be less than 0, we say that our system is under stable condition, and if it is greater than 0, we say that it is unstable condition, right? So that's how you have to do. First you have to linearize these two, and then you look for the condition where real up to what condition the eigenvalue, real part of eigenvalue is less than 0. Okay, so that stability of the vehicle can be maintained. And you will know that like I'll just go here. So here you see that, peak. So as long as your vehicle is operating up to this, you that lambda, a real part of lambda will remain negative. The moment it crosses, it means the slope here is positive, and here the slope becomes negative. Means if you try to find out d mu by d lambda, mu is your coefficient of addition of the tire and road interface, and lambda is the speed ratio. So you see that as long as it is positive, your vehicle will be stable, and the moment it become negative, it will be unstable state, right? So that's how things works out mathematically also, if you try to do it. But the important thing is that this curve is very peculiar for the tire and wheel interface, right? And here you see that this peak value reduces based on the type of the road. Here it is dry road, here wet road, unpacked one, the ice road. So that's why you see that we can't really increase the speed of our vehicle when the road conditions are different. So for ice, a tire cannot afford to go beyond this. Okay, so hence the speed limit is also there. So all these characteristic that we get, ultimately it will go here, and you will get Ft. Ft is the tractive force that we get, and that's what was used here. Okay, so again this is a non-linear term, right? So everything needs to be done, and then you can make the model in Simulink, like is a wheel dynamics, is a vehicle dynamics, this is your tire road interface. You can connect all of them and try to get the wheel speed, vehicle speed, and all that. So that is one way you can just try to do. So these are all linearization that is being done, and what I was talking about, this one, right? This is your lambda component Jacobian, and lambda of this real, so real part of lambda is given by this. So here you see that you have dou mu by dou lambda term. Okay, so it says that when dou mu by dou lambda is positive, eigenvalue have negative real part. It means that it's stable. If it is negative, eigenvalue have positive real part for only this condition. So under this condition, your vehicle will be unstable. Okay, so that's how we try to do stability analysis of vehicle based on this characteristic curves of tire and road interface. Okay, so that is more or less the part of it. There are many other example available. Like I'll not go into much detail of what are these because of the time limit. But what I will tell that the major part of this modeling is the drive line. One was your finding out acceleration and other thing, and second is based on the drive line we do all the modeling. For example, starting from your engine, then clutch, then transmission gear, then propeller shaft, final drive shaft, and the wheel. For all the components we try to write the equations separately, and then you can again transfer them into some kind of Simulink model or 1D model similar to this using the available thing. So in MATLAB, basically there are two types of system available. One is your Simulink, another one is SimScape, which is also called the physical model. Okay. So Simulink, this is your Simulink model. Okay, it appears like this. But SimScape will have block, physical block like this, and uh, you can define straight away the datas and all. These are the wheels, front wheel, rear wheel. This is the car body, wind speed, engine input you can give. So many things you can just do it using your simscape, and you can just see, like we did it for some cases, and we found that both the results will come out to be same because it's not a difference, but it is more convenient. Simscape is one which is going to stay, many people use it, so you should try to explore this Simscape version of vehicle dynamics modeling. So this is another example where we did some four-wheel drive condition. So all the full model, full vehicle model, right? So this is your wheel, this is your wheel, front wheels and the rear wheels. You have differentials, gearbox and all, engine. So that way you can, make a complete block of the whole vehicle using this SimScape. And I recommend that you should try to use it. Another thing is you can interface, car sim that we do with Simulink or Simscape also, and you can visualize, for the visualization. So whatever changes are happening in Simulink, that you can transfer it to the model in the car sim, and you can visualize the motion of the vehicle on the road condition that is being there, and then see how each components are varying with time. That can also be visualized nicely in the car sim. Okay, so here the coupling of these two things are happening. Then the modeling of motorbike using bike sim, that is there. Here the influence of wheelbase that we have. So what happens when these wheelbase changes? So here you can just see. So let us say for a given condition, uh, after certain speed, you will see that there is an instability that is happening. You see that this is just increasing, and the vehicle just go into some unstable state slowly, and then it falls down, right? Now if you just have little wider wheelbase, so in that case, you see that you will be able to maintain the speed, and whatever the excitation was, it will just zero down, right? It will not amplify, and that way the stability is maintained. Yeah. So with this, I would like to conclude and stop. That so there are very fundamental forces that you need to understand, and then make use of some important softwares to appreciate the whole vehicle dynamics. Uh, so these are the tools that you should use if you are interested in doing vehicle dynamics. With this, I would like to thank you, and if you have any question, you can ask me.
Hello.
Yeah.
Hello. Sir,
Yes.
it's you have mentioned all the things related to the linear and nonlinear frequency
1 minute.
training in MEMS. So, sir, I would like to ask one question as I'm a junior engineer. So, if you want to do the research in in this particular respective field, so what initial steps I have to taken into considerations for it, or the research point of view?
In the vehicle dynamics.
Yes, sir. Vehicle dynamics.
Yeah, so you have to first learn dynamics, okay, vibrations and dynamics course, and then you should learn MATLAB, how to do simulation in MATLAB. I think with these two knowledge, you will be able to start. The vibration and dynamics is the most important subject that you need to consider. A little bit of basic of controls should also be, because ultimately you also have to design control. And as far as the tool is concerned, it is always better to start with the MATLAB. Okay, that is available everywhere. Now, those who are not having access to MATLAB, there is a freeware that is available, like Modelica, like Simulink. There is another model called Modelica, which is completely free, and you can use it and try to do the modeling. So I think these three things should be enough to start with.
Okay.
Learn
Thank you so
MATLAB.
much, sir.
Yeah, yeah.
Yes, sir. Go ahead, sir.
Yeah,
Saying
learn
something.
MATLAB and learn dynamics and vibration. Based on that, you can always try to work in vehicle dynamics.
Okay, sir. Okay. Thank you so much, sir.
Thank you. Is there any other question?
Okay. Sir, I conclude the session.
Okay.
Uh, it's great privilege to having you, sir, here for sharing
Mhm.
your experience with us.
Thank you very
Uh, it
much.
it has been very informative and knowledgeable session. It was great, excellent presentation from starting reference book, labs, journals, and then vehicle classification based on size, number of
Mhm.
axles, and importance related that, and then fundamental definition related to vehicle dynamics, physical condition, dynamic behavior, and force act on the vehicles, various force where acts and how we simulate these forces, and then equation of motion and test. Then testing related vehicle in that tire testing means importance of tire testing and tire track to braking forces. What are the forces acting on it? Once again, thank you very much, sir,
Thank
for
you so
accepting
much.
our request and sparing valuable time with us.
Thank you so much. So tomorrow I have at 12:30 or 12?
12:30.
12:30. Okay. Okay. Thank you so much.
Thank you,
Bye.
sir.
Hello, Sanket. Hello.
Yes, sir.
Is there any instruction for the participants?
Just a minute, sir.
Hello.
note of it. Hello.
Yes, please go
Uh,
ahead.
yes, sir. All the participants, you have one there is one announcement. Feedback and attendance link will be shared on your registered email ID shortly. And tomorrow, first session will be start sharp at 10 a.m. Thank you for attending the today's sessions. Thank you, everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.